Welcome. Today's notes worksheet is entitled Polynomials Day 2. We will just continue working with the polynomial expressions from yesterday. In particular, we'll be looking at some of the multiplication and division that go with polynomials. So let's get right into it. At the top of your page there, I see something along the lines of special products and just some patterns that come up working with some polynomials here in terms of multiplication. So let me just kind of read what we have, and then we'll go ahead and put a couple examples in place. So the first one is what is called the sum and difference pattern. And so this would be two binomials multiplied together, one obviously with the plus, one obviously with the minus. We would FOIL, and what happens is the outside and inside end up canceling, and you end up left with this expression right here. We will actually name this expression in the next couple days, but for right now, the sum and difference pattern produces these two squares with the minus right in between. So something nice and simple. I just have this on my paper, so I'll just offer this one up. If you want to come up with a different one, that's perfectly fine. So again, just two binomials multiplied together. Same binomial, except one's a plus, one's a minus. And so it turns out to be the first one squared, and then minus the second values squared. Nice and easy. All right. Now the next order of business is to get into this expression right here. You'll actually hear me use this phrase over the course of the semester, what is called the square of a binomial. And this should look pretty familiar there, meeting that phrase nicely. So here's your binomial and squared. Now remember, just in terms of exponential properties, I can't just take a squared and b squared. So remember those exponential properties. There's a product property, there's a quotient property, but there is no sum property or difference property. And so this is how it would play out for the square of a binomial. And so you end up getting this middle term right here. So again, I'll just throw an example in. I have this on my paper, just x minus 3 squared. That would be the square of a binomial. And if you were to kind of expand that out, you end up getting the first term squared, and then you end up getting a middle term here, and it's just the 3 times the x, and as you can see, times a 2, so it becomes times 6x. And you can explore this in a little further detail if you'd like. That's fine. We'll actually look at a geometric interpretation of this momentarily, but for right now, that's just a nice quick example of it. Good. And then this one, a little obscure, but kind of in the same vein, we had square of a binomial and now so cube of a binomial. And notice the expansion is quite complex. So if I asked you to do a binomial cubed, it's not just a cubed and b cubed. As you can see, there are several terms to that. And so there's just a particular pattern that goes with this, and here's the pattern that's in play. We will explore these binomials expanded later on this year, and we'll look at this in a little more detail. In particular, I'll kind of show you where the 3's come from. For right now, I guess we're just going to have to take it for granted that this is the case. So this pattern, even though it's not ideal, is at least a shortcut from doing a plus b times a plus b times a plus b. Which, I guess theoretically you could do that if you wanted to. But let me go ahead and put an example in, show you what I have, and then we'll do a couple together there, see if we can get this going for you. So if I did x plus 2 cubed, what it basically says is there are 4 terms to it. So we're going to have this term, this term, this term, and this term. And the way this pattern just plays out, and that's basically what we're looking at here is multiplication patterns. It is the x cubed to kind of start it out. And then we get a coefficient of 3, and the x cubed becomes x squared, and then that 2 kind of pops up for the first time, and so kind of a times the 2 to the first there. And then, same deal, the next term in our polynomial, the coefficient of 3, we went from x cubed to x squared, then it goes down to x, everybody. And that 2, it was 2 to the first, now it's 2 to the second. So something like that, and again, this is all just multiplication right in between for those terms, creating each and every term of this polynomial. And then last but not least there, you see it's just the back end, and it would be the 2 cubed. And so that's how this would play out if I expanded it using that pattern, rather, again, than doing x plus 2 times x plus 2 times x plus 2, in the same vein of yesterday, kind of that polynomial multiplication. So anyway, let's finish this one up. This would be x cubed. 3 times 2, everybody, is 6, so I get a 6 times the variable squared. And then over here, numerically, 3 times 2 squared, so 3 times 2 squared should give me 12 times the x, and then plus 2 cubed, which is 8. And as a matter of fact, that would be this right here expanded out. Again, later in the year, we're going to do these binomials raised to the 4th, to the 5th, to the 6th, and there are really some incredible patterns that go with it. But right now, as you can see on your paper, it's square and cube. Okay. Well, let's do an example there. It'd be great if, maybe I can do that first one, letter A, and then, maybe you can pause the video and try B and C and fast forward it and, just see how you did. But let's go ahead. Let's start it out here. So cube of a binomial, and I'm going to just follow that pattern here. And basically it just says, okay, take the first one and cube it. Now with minus, we do have to be a little more careful with the sign. So if you look above there, it should be x cubed and then a minus, and then coefficient of 3. The x cubed becomes x squared, and the 4 pops up for the first time. Then, looks like we have a plus. Another coefficient of 3, the x squared becomes x, everyone, and the 4 jumps up to 4 squared. And then last but not least, got a minus on the back, and just your 4 cubed. And that's it. That's pretty much our 4 terms in a nutshell. First and last should be pretty straightforward for you. I think it's those middle terms that you're just going to have to kind of deal with. And again, please ask questions. Let me know if I can help on that piece. But that's how it would expand out. And then let's go ahead and simplify, of course. X cubed right there, 3 times the 4, so I'm getting a 12x squared right in the second term. And then plus, I'm getting a 3 times 4 squared, so 3 times 4 squared should be 48, so 3 times 16, and then times the x, and then 4 cubed is 64. And that should be our winner right there. If you take a look, again, kind of rewind that or pause that just to make sure it's all clicking there. But cube of a binomial translates into 4 terms in standard form, and that's how we get our 4 terms. And you can see really nicely it works well in standard form. Here's your x cubed, x squared, x to the first, x to the 0 on the back. Nice. All right, I'm going to do letter B, but I would encourage a little pause at this stage and see if you can pull it off on your own. You're going to have to be a little careful with this one because of the 2x as representing the first term of the binomial, but hey, let's see what you can do. So I'm going to go ahead and do this. So it's 2x cubed. That's how it's going to start out, everybody. So it's the whole thing. Notice I put it in parentheses there, and I'd encourage you to do the same. And then here we go. Let's go ahead and get our coefficient of 3. The 2x comes down to the second, and the 1 pops up there. And then let's keep that going. It's all patterns. We stay with the 3. The 2x comes down to the first. The 1 jumps up to the second. And then last but not least, I've got my 1 to the 3rd power. All right, so there we go. And that would be our cube of a binomial, which we're going to have to simplify. Notice a lot of overlap already with what we're talking about here. Here's a nice little product raised to a power. We dealt with this exponential property, so that should be 8x cubed when I do remove the parentheses. Let's see if you can play this one out. This is nice right here numerically. I have a 3, and remember to remove parentheses, we're going to take each of these to the 2nd power. Product raised to a power. And so 2 squared is 4 times 3 times 1. I'm getting a 12, and then of course the x was squared as well. Nice. I'm going to continue here. Let's get this term taken care of. I've got a 3 times the 2 times the 1 squared. And so numerically it's 6 and times the x, and this wasn't raised to a particular power, so that's good. And then last but not least, 1 cubed is just 1. And that is how it would expand out. Let's box that up. Feeling pretty good about it. Nice. All right, so 2 out of the 3 taken care of at this stage. This is probably, relatively speaking, trying to keep the numbers simple for you. So this is, a good culminating problem here as we finish up these cube of a binomials. So just be careful with the name of the expression and how it translates. In this case, we're expanding it out and putting it in standard form. This would be considered, as a matter of fact, factored form. All right, let's do the last one then. If you haven't already, play it along with me. So I take the first term and I cube it. The whole 3x has to be cubed. Minus in the middle there. Let's put our coefficient of 3 in place. Now here's what happens. That 3x goes from being cubed to now being squared. And then the 2 pops up. All righty, good. Now a plus. Let's put that coefficient of 3 in place. I'm putting the 3x in. And how does 2 squared sound to you? All right, notice those 2 terms. I think that's the key for these. See if you could pull that off. And then last but not least, looks like just 2 cubed there. Something along those lines should do. And then it's up to us to just simplify that piece right there. We have 1, 2, 3, 4 terms in our polynomial. This should work out pretty well. I'm getting a 27x cubed with this one, 3 cubed and x cubed. Now here, just let's be careful numerically. See all the numbers play out. This is a product raised to a power, so I would have to do my 3 squared and x squared to remove the parentheses. So this really is 9 times the 3 times the 2. And so 9 times 3 is 27, times 2 is 54. So I'm getting a minus 54x squared. Cool. Let's keep it rolling. 3 times 3. We can remove those parentheses now. It's not raised to a power. So 3 times 3 is 9 times the 2 squared. And so that looks like a 36x on that. And last but not least, I'm seeing an 8. And there, I think, is your expansion perfectly written in standard form. All right, good, good, good. So just some good things there with those special products. Obviously, we talked about the polynomial multiplication on the previous notes worksheet. Just trying to put together a few more, just a few more patterns that you see. Okay, so I'll be fairly quick with this one. It's just a nice way to see, provide a little geometry connection if we can. So it says, use the tile drawings given by the teacher to provide a geometric interpretation of the square of a binomial. All right, so here's what I'm thinking here, guys. How about this? Can you draw just a big square on your paper, if you would? Something like that. And then here's how we're going to do this as best as possible. Let's try to draw a square kind of like that, give or take. And let's label this square A by A. Something along those lines would do. And then if you get an opportunity, we're going to go in the lower right-hand corner here, and we're going to do a secondary square. And this one I'm going to do B by B. That should play out pretty nicely so far. There we go. And then if I put a few other things in place then, and you know, you can do this or not do this, I'll leave that up to you, but I'm going to label that B. Obviously if this is B, then this is B up here. And just kind of seeing some other things to label. If this is B, then this would be B over here. And, you know, I'll throw an A in just for kicks over here as well, and down there. So everything's labeled. And I guess here's what I would ask us. I would ask us to find 2 ways to come up with the overall area of the big square right here. So if you look at that, I would ask you, could you come up with a couple different expressions for the area of that square? So the first order of business, I guess, is to talk about just the area of any square is really just the side times itself, length times width again. And, you know, I guess what would be the length here, which obviously is the same here. And I'm hoping you would agree it's A from here to here, B from here to here. So all the way down, everybody, would be A plus B. So the way I'm seeing that, to get the area of the square, we would take A plus B times, of course, this other side here. And because it's a square, it's the same. So A plus B times A plus B is A plus B squared, which, as you can see, of course, becomes a beautiful looking square of a binomial. I'm hoping everyone's okay with that piece. Now what I would love for us to do is come up with an alternative way to come up with the area of that big square. And what I'm thinking is, let's see if we can just add up all the individual pieces together and see what that would include. So here we go. Here's a square right here, of course, which is A by A. That's A squared. Here's another little square right down here, B by B. So that's obviously B squared. And you can kind of see that there's more to it. So remember, we kind of talked about this before. It's not just A squared plus B squared when you have a sum raised to a power. There's more to it. And as you can see, here's your A squared, here's your B squared, but there's more to it. And do you see a rectangle right here? A by B. And do you see a rectangle here? A by B. And how many of these do we have, of course? We have 2 of them. So I gave you that little pattern up above here. I just wanted to at least provide a little geometric representation of where that comes from. And so please, I've seen this a lot over the years. Students want to shortcut this, taking just a squared and b squared, but you can see there's more to it. And same with on the cube. Okay, very cool. So again, hope that just really solidifies those ideas from the top. Let's see if we can move forward. So the last operation that we'll take a look at here will be the division. And so what I figured we would do is really just bring it on back a little bit, go very concrete. So when we go abstract, we can just follow the same process and just obviously increase the level of difficulty. Okay, so let's do it. Investigation. Remembering the division algorithm from elementary school, how do we perform the following operation? So what I want to see is how many times 21 divides into 658. So how many groups of 21 are there in 658? Well, I can't pull that off right away, but what I can do is break this on down. So the way I would play this out is I would just say, okay, I don't know how many times 21 goes into 658, but I can figure out how many times 21 goes into 65. So I'm going to simplify it a little bit. I'm going to just break it down a little cleaner for me. And 21 goes into 65 exactly 3 times. Well, sorry, not exactly 3 times, but it goes in 3 times. So I put my 3 above where the 5 is, and if you remember correctly how this plays out, everyone, I multiply this back down, and kind of get used to this if you could, because this is exactly what we're going to do. And I would ask you this: what operation do I do with the 65 and the 63? And if you remember, of course, it's subtraction. And so I subtract going right on out in front. 65 minus 63 is 2. And then if you remember correctly, we bring down that 8. And then, as you recall, of course, I repeat. So now I'm looking at how many times 21 goes into 28. And it goes in once. And so now if you remember, bring it on down. Again, see the algorithm, guys, because we're going to repeat this when it gets very abstract on the back side. And so 1 times 21 is 21, so that goes right here. What operation comes out in front, everyone? Subtraction. And then 28 minus 21 is 7, and that is looking great. And I would theoretically repeat. I would ask myself, how many times does 21 go into 7? And it doesn't. So I guess I would ask you this: what does the 7 represent then in terms of our answer? It represents the remainder. Cool. So let's go ahead and write a few things down here and just get our bearings, and then we'll get a little abstract on the side. So this is basically the operation I did. I did 658 divided by 21, totally arbitrary. So how many groups of 21 are there in 658? Well, there are 31 groups of 21, and there were 7 units left over. Is everyone okay if I kind of write it like that? Now, here's what I'm going to ask you to do. Put a little or on your paper for me, and let's express this in a slightly different fashion. So again, when it gets more abstract, it'll at least make sense that that's the way that we would express it. So instead of saying there are 31 groups with 7 units left over, we could say there are 31 and how many groups left, or how many groups remaining, or what fraction of a group is next. So I guess the way I would say this is that there are 31 and 7/21 groups of 21 that go into 658. So there are 31 and, I know this is 1/3, of course, so there are 31 and 1/3 groups of 21. Everyone okay with that? And again, if you want to go ahead and maybe put a little, just very lightly, put a little 1/3 right there. You don't have to if you don't want to. Obviously, the 7/21 reduces. Okay, I hope that kind of makes sense in terms of what we're looking for in terms of division, and then also how to express our answers and all that stuff. Just a couple things that I need to put down here, and then we'll keep it moving. So just, if you remember the buzzwords from division, and we'll see this in the future as well. We're going to do quite a bit of division later on this semester and early into second semester. But 21 is what we would call the divisor. The 658 is what's called the dividend. If you can just quickly jot this piece down, and then I'll keep it moving for you. that 31, our answer, so to speak, represented the quotient, and of course the 7 represented the remainder. All right. So how many times does 21 go into 658? 31 1/3 times. Okay, perfect. You have on your paper here, check each answer with the fact that, and here's what I would say. Again, just kind of going back to that elementary school algorithm, multiplication and division go hand in hand. So when we did this divided by this is equal to this and that left over, really, again, here's how I would say it. This is made up of these two multiplied together. So we would read this as the quotient times the divisor, and then there's a little left over, so plus the remainder. So something like that would do. Quotient times the divisor plus the remainder. And just in this case, if you want to just write this down lightly, and I'll see if I have my graphing calculator set up here, maybe I'll bring that up. But I would say that 658, what that really means is equal to 31 times 21 and plus the 7. Again, just kind of old school calculations there, and seeing the idea of multiplication and division working hand in hand. Well, let's go ahead and take a quick peek. So as I said, that 658 should be made up of 31 times 21 plus the remainder of 7. And there it is. Cool. All right. So very concrete initially because it's going to get abstract momentarily. And just keep in mind how I did this. I promise I won't change anything. But again, it's all variables the rest of the way here. Well, let's go give it a try. So that last operation is dividing polynomials. And we're going to do the same thing, guys. We're going to break it on down. In fact, we're going to really break it on down. So here's what I need you to write. Begin with the leading term of the divisor and the leading term of the dividend. That's all we're going to do. So leading term of the, there it is, dividend. And so we're going to do 2 together there, just to kind of take a look at it. And we'll perform it in a very, very similar fashion, just kind of the long division there. How many times does x squared plus 1 divide into 3x cubed plus 4x squared plus x plus 7? As you can see, quite a bit more abstract than what we kind of talked about before, but we're going to do it the same way. So here we go. Let's go ahead and set it up. Leave a little room up at the top if you would. I have x squared plus 1, and that's being divided into 3x cubed, 4x squared, plus x plus 7. Okay. That is outstanding. And so this is our divisor. This is our dividend. Let's go get our quotient and see if there's any type of remainder there. And notice what I wrote up above. I can't pull this off just single-handedly right here, this into this whole thing. So what I'm going to do is just focus my attention on the beginning piece. So here's the leading term of the divisor. Here's the leading term of the dividend. I can do this. How many times does x squared go into 3x cubed? Another way to say it is x squared times what is 3x cubed? If you still can't pull that off, that's quite all right. What I'm basically saying is this divided by this. And I'm just going to work off to the side just in case. If you know what you're doing here, perfect. But basically, that's what I'm asking. How many times does x squared go into 3x cubed? And this is something you've done before, nice and easy. 3 divided by 1 is 3. What's x cubed divided by x squared? It's x to the first because I subtract exponents. So you can see all of the overlap here with some of the lessons we've had already. So this is really just an exponential property when you really break it down. So long story short, how many times does x squared go into 3x cubed? 3x. All right, now I'm going to just do some erasing with this. If you need to kind of write this stuff off to the side, please do so. I don't want it to get in my way, so away it goes. All right, now what do I do with this? Think about what I did when I did that concrete problem. Hey guys, all I do is I multiply this by the divisor. I want to bring something back down here. So what I'm going to do is take 3x times this right here. I'm going to distribute this into this divisor. So 3x times x squared is 3x cubed, and that's what we wanted to have happen. 3x times 1 is 3x. Let's put it under its like term. Apples to apples, everybody. So we're going to be doing addition and subtraction here. Well, specifically subtraction right now. So please just make sure you line it up appropriately. Good vertical method on this. All right, hey guys, it's just top minus the bottom. Be careful, this is probably where I see most mistakes. So this minus this cancels. They're gone. 4x squared minus 0x squared is 4x squared. Here's where I would see the mistake, everybody. It's 1x minus 3x. Be careful, minus 2x. Most definitely. And then 7 minus 0, still 7. So that's the key, guys. Subtract going right on down. This, and then there it is, minus 2x. Please be very careful on that. Okay. What did I do when I did the concrete problem? Hey, guys, all I did is I repeated. And so now I'm just taking a look. How many times does x squared go into 4x squared? And if you're not sure, just off to the side. So how many times does x squared divide into 4x squared? 4 divided by 1 is 4. X squared divided by x squared is x to the 0, or just 1, so it's just 4. And there it is. There's my 4. All right, let's get rid of this flack right here and keep it going. So what do I do once I have this piece of my quotient? I have to multiply it back on down. So guys, multiply it into the divisor, the whole thing. Think of it as distributing it in. 4 times x squared is 4x squared. 4 times 1 is 4. Put it under its like term, please. Minus goes out in front. Again, haven't changed anything from the front side. That's the good news with this. Obviously, it's a little harder, though. When I subtract, those cancel. Negative 2x minus 0 is negative 2x. 7 minus 4 is positive 3, and that's looking good. Think about it here. I would repeat. Does x squared divide into negative 2x? No. And so what does this negative 2x plus 3 represent? The remainder. So a couple ways to kind of write this. I'm going to try to get you going on one way. So how many times does it go in? It goes in 3x plus 4 plus a fraction left over of the divisor. So that's what it would look like. This is the remainder, and so this is the fraction of how many more groups we would have. So 3x plus 4 plus negative 2x plus 3 over the x squared plus 1. Let me just go back aboard real quick. Exactly right here. It went in 31 plus 7 over 21 times. That's how many times, or that's our full answer right there, quotient with the remainder over the divisor. And that's just what I did here, guys. Quotient plus the remainder over the divisor. So if you wanted to write remainder negative 2x plus 3, not the end of the world, I like it like this for the time being if you can. All right, there you go. One time, pretty good. Let's go try another one. Now, if you would, on this one, how about right over here, give me an asterisk. There's one little catch on this one. So there's just one piece on this one that we have to be extra careful on that did not occur over here. So look at that dividend, everybody, if you would, and can you kind of take a look and see what the fundamental difference is between this dividend and this dividend right here? And if you look at this dividend, it starts at 2x to the 4th and then jumps down all the way to just a negative 2x to the 1st. And so even though they're not written, there are cube terms, square terms that we have to account for. So I guess long story short here, include placeholders. It's just the best way to keep everything as organized as possible. So include placeholders, please. And I'll show you what that looks like. Let's go get them. A nice easy divisor here, so this shouldn't scare us too much if we do our placeholders correctly. So here we go. I do have 2x to the 4th. And again, even though it's not written there, I do have 0x cubed. And I think it helps to write it like that. And then I have 0x squareds minus 2x's, and how about a -1 unit on the back there? And that's our dividend in a nutshell. It's a lengthy one, but I think it's now going to help us pull this off. All right, let's go get them. Nice and straightforward. How many times does x go into 2x to the 4th? Again, if you can do it, get going on it. If you can't, this is what you're thinking of right here, something like that. How many times does x go into 2x to the 4th? 2 divided by 1 is 2. X to the 4th over x to the 1st is x cubed. And so the first part of our answer, 2x cubed. No question. All right, say goodbye to that, and let's go keep it moving. What do I do with this 2x cubed? Well, I multiply into the divisor. I distribute it in, and I get 2x to the 4th minus 2x cubed. So notice, look how nice that is, the vertical piece. Align those nicely. That's what the nice thing is about that placeholder. All right. Minus out in front, guys. Let's get it going. These are going to cancel. Just be careful. As I said, minus, it's a killer. 0x cubed minus -2x cubed. So how many x cubes do I want to write here? Positive 2. So see that piece, everybody. 0 minus -2 is 2. Now let's repeat. Again, if you need to work off to the side, please do so. How many times does x go into 2x cubed? Well, 1 goes into 2 twice. X goes into x cubed, x squared. And now we're not doing a nice job here. Let's keep it going. So 2x squared times that. Let's see. Oh, I'm sorry. I forgot something here. Let's do this first. Let's bring that on down. There you go. That's a little better. Now, I was so focused on that, I forgot about this piece. So now, guys, let's distribute that in. And we do get our 2x cubed. And how about a minus 2x squared? Looking good. Again, it's just operation and then repeat. Here we go. Subtract. Those cancel. 0x squared minus -2x squared is 2x squared minus 2x minus 1. We're getting close. So how many times does x go into 2x squared? Should go in 2x times. And now repeat, guys. Distribute that into the divisor. 2x times x is 2x squared. 2x times -1 is -2x. All right, put my minus. Those cancel. Ooh, this is kind of nice. These cancel, and I'm left with just a -1 right there. Sounds good. And as a result, does x go into -1? No. You know, we would just have this underneath that, essentially. So final answer, when all things are said and done, I've got 2x cubed plus 2x squared plus 2x plus the remainder over the divisor. That's how many times it goes in. It is abstract, absolutely, but we're going to be doing some work with division over the course of the year here, and kind of understanding this algorithm will help get us in that, be successful with that stuff. Okay, take a look. So 2 right there. Obviously, you'll get a little practice on that piece. I've got just one more thing to take a look at. We'll be fairly quick on this, and then just kind of move forward. So remember the idea. Dividend, let me just write it one more time here, is equal to the quotient times the divisor plus the remainder. So it does say check your answers here. Let's do it at least once, and we can kind of go from there. So let's go for it. Here we go. I don't mind doing it one time with you. So quotient for letter A was 3x plus 4. Divisor was x squared plus 1. And the remainder was -2x plus 3. So working with polynomials, again, multiplication and division really go hand in hand here. And we do have some abstract expressions with this, but these are things that we can manipulate. So how would I go ahead and do this? Well, I would probably multiply first. Multiply comes before addition, of course. So I'm thinking a little foiling on this end, and then we'll combine anything together on that. So let's see what we end up getting. FOIL, I get 3x cubed. And let's see, I'm going to just go ahead and do this in standard form. I've got a 4x squared plus a 3x and plus a 4. And then plus negative 2x plus the 3. So I FOILed right there, got that piece. Let's combine any like terms now. It looks like I have 3x cubes. I have 4x squareds. I have a 3x and a negative 2x added together, so I have a 1x and a 4 plus 3. And I can't see it on my board here, but I'm going to go back and take a look. Was that equal to the dividend? Here is our moment of truth. Take a look, guys. And there it is. So I like that piece. Is it necessary? No, but I mean it is a way to check, did we do everything correct? Could we do the same thing on B? Yeah, sure. But I think I'll hold off. I'm sure we did fine, and kind of bring it to a conclusion at this point in time. All right. Well, get some practice on the division. Let me know if there's a particular step that you didn't quite see, and I can walk you through, of course. Thanks for listening.